Hey, John here. I actually purchased this thing some decades ago, which includes this CD-ROM right here. Among other things, it includes the source code of this book right here, of which chapter 20 right here, looks like I bought it on Amazon back when they described themselves as a bookstore with 2.5 million titles. That'll be, that was a while ago, right? Now they got everything. Anyway, the point is, this includes a paper called an Introductory 4.4 BSD IPC Tutorial, Inter-Process Communication Tutorial. This is what I want to talk about today. And the reason for the long-winded beginning is because of this license right here. This is what we call the 4-clause Berkeley license. Very common all over the internet, okay? This is the license that covers the actual source code of chapter 20 of the book, as well as the diagrams in it, which is what the code is that I want to talk about today. The bottom line is that the license allows redistribution in source and binary forms with and without the modification, provided that the following conditions are met. 1, redistribution of the source code must retain the above copyright notice. If you redistribute it in binary form, you must reproduce the above copyright notice. List of conditions, following disclaimer. All advertising materials must mention this. This product includes software developed by the University of California, Berkeley, and its contributors. Clause 4 says neither the name of the university or the names of its contributors may be used to endorse or promote products derived from this software without specific written permission from Berkeley, prior written permission, which I can assure you I do not have. All right, so the big disclaimer is this software is provided by the regions and its contributors as is, and any express or implied warranties, including but not limited to the implied warranties of merchantability and fitness for a particular purpose, are disclaimed. In no event shall the regions or contributors be liable for any direct, indirect, incidental, special, exemplary, or consequential damages, including but not limited to procurement of substitute goods or services, loss of use, data, or profits or business interruption, however caused on any theory of liability, whether in contract, strict liability, or tort, including negligence or otherwise, arising in any way out of the use of this software, even if advised of the possibility of such damage. I think I've more than covered my responsibility of disclosing that particular copyright. As you go down here, you can clearly see this is an NROF document that describes the 4.4 BSD IPC tutorial in Chapter 20. And this is what it looks like when you render it to a PDF. Its age is starting to show, but TCP sockets are still based on the contents in this tutorial. These are the so-called BSD socket API that all the big OSs that you're familiar with still use today. Now, this document covers, as they say, several choices for inter-process communication. Today, I'm focusing only on TCP, which we'll see is what this document refers to as a stream communication in what they call the internet domain. Now, as it says right here, that the inter-process communication facilities were originally added to the 4.2 release of Berkeley Unix in the mid-80s. And as we'll see when we walk through the code, the basic idea of the interface was to make the inter-process communications, the IPCs, look a lot like regular old file I/O. And we'll see how that manifests itself when we work on the code, because it'll be using reading and writing, much like you would regular files, or printing to the screen and reading from the keyboard, in order for two processes to communicate with each other. Now, as they describe down here, originally, inter-process communication was limited to processes communicating within a single machine. But with Berkeley Unix 4.2, when they added the socket API, you can use inter-process communication between separate machines by way of the internet. Now let's skip down here to section 5. The previous sections talk about those IPCs that communicate within the machine. Again, we're going to talk about the IPCs that allow us to use the internet domain to communicate between machines. Well, let's make sure we got the terminology down here, okay? In Berkeley Unix 4.4, what happens is you can create a thing called a socket. You can give it a name, and then you can use it to send messages between two sockets. Now, in this document, they refer to the socket as one of the endpoints of a stream of communication between two applications. Therefore, each of the two applications has one socket, which represents kind of the end point of that stream. And therefore, those two sockets are connected together. Now, I punch this point because it's very common to hear people refer to a socket as the entire stream, including both of its endpoints, when they speak of communicating between two processes using an internet domain stream. Technically, the socket refers to one end or the other of that stream. Now, as we'll see, the BSD socket API uses the word name to refer to what we'll see is an address of each of the socket endpoints. Now, they go on to say that the space from which the address is going to be drawn is referred to as a domain. Now, don't confuse the word domain in this context with something like a domain name, like google.com. All right, those a domain name in the internet you might put in your browser location bar, a URL, is totally different than the domain, which we'll see, of a set of protocols that are used when addressing a socket. Okay. They go on to say that the Internet domain is the Unix implementation of the DARPA Internet Standard Protocols for IP, TCP, and UDP. We are concerned right now with TCP. That's our main focus right now today, okay? So it then makes sense to say that the addresses in the Internet domain, right, and the Internet protocols, consist of a machine network address and an identifying number called a port. And we'll see all about that in a minute. And then they close the paragraph with the observation that the Internet domain names allow communication between machines. Okay? Now, again, the word domain here and domain name, don't confuse that. The domain name here is referring to the IP protocol and the TCP stream and stuff like that. Goes on to say the communication follows a particular style. Currently, as of like 1986, and even today, most communication that's used on the internet is either through a stream or by datagram. And we'll see that stream-based communications are TCP, and datagram communications are UDP. And then they observe that stream communication implies several things. Number one, communication on a stream takes place across a connection between two sockets. The communication is reliable, error-free, and, as in pipes, which are discussed earlier in this document, which is basically a stream of data flowing from one process to another, no message boundaries are kept. And by that they mean if I write, say, 100 bytes into one end of the socket, the other end of the socket might end up reading 2 blocks of 50 bytes to get that 100 bytes. The boundaries is what they're referring to. No matter what I write into one end of it, however many bytes, all the bytes will get to the other end. But just because the receiver says, hey, I want to read a message, you're not going to get the number of bytes, not necessarily anyway, that matched the number of bytes wrote in the other end in each individual call to read. We'll see more about that in a minute. And they observe that reading from a stream may result in reading the data from one or several calls to write on the other side of the socket. Okay, that's what they're talking about right there. It then proceeds to describe why we consider TCP to be a level 4 protocol. The protocol implementing such a style, namely a stream, will retransmit messages that are received with errors. It'll also return error messages if one tries to send a message after the connection has been broken. Okay? That's your layer 4, making sure that the data arrives in order without missing gaps, and attempts as best as it can that it reliably gets them from one end to the other. Obviously, if you unplug your computer, it clearly cannot send the data, right? So when we say reliable, it is reliable within reason. It then goes on to talk about datagram communications, which does not use a connection. Therefore, even though it's kind of considered a layer 4 protocol, it doesn't have any of the real services that are affiliated with it. Each message is then addressed individually. If it's correct, it'll generally be received, although it's not guaranteed. So when we talk about datagrams, and this is why we're not going to get into the details here, it is not a stream. it is not guaranteed to be received on the other end. It's almost a layer 3 protocol. Now, as we approach section 6 here, it says 1 specifies the domain, style, and protocol of a socket when it's created. We'll see all that when we get to the code that we're going to walk through in a minute here. Now, as we scroll down, we see a section that talks about datagrams, which we're going to kind of gloss over here today, but there's some information in the bottom of the paragraph down here that applies exactly the same to streams as well. So let's pay close attention to these last 2 lines down here. Implicitly, an internet address, when they refer to one end of a socket, that socket has an address. Okay? It is a triple that includes the protocol as well as the port and machine address. Those 3 things combined represents the address of a socket, or, in this particular case, the source or the destination address of the datagram. It then goes on to say that an association, which is between the 2 socket endpoints of what we're going to see as a stream in a minute, is thus identified by a tuple. That is the protocol, which has to be the same for both ends of the stream, for both sockets. Have to be the same protocol, otherwise they can't talk to each other. The local machine address and the local port number, and the remote machine address and the remote port number. Again, I just want to introduce some terminology before we get to all the details here. Now, as we approach section 8, where we talk about connections and streams, which is where we want to go to, all right, you will see a paragraph here that gives you a little bit more definition of what the port number refers to, okay? And they specifically say a port number can be thought of as like a mailbox, all right? And I like to think of that as like a P.O. box. The address of a machine might be like the address of a whole post office. But a P.O. box within that post office represents one of many different things that you can communicate with, even though they're all in the same post office. The idea is that that's where the messages flow, or as we'll see when there's a stream, that's where the data in the stream will flow. Then goes on to say this is still true for historic reasons, although the rationale for it's kind of gone now. The so-called well-known port numbers still exist. The idea is that it used to be that those low-numbered port numbers were reserved, and that the sheer cost of the machine would prevent anybody from being rogue out there and just starting up services on these low-numbered ports and wreaking havoc with anybody else on the internet. It then goes on to say that higher numbers are available for general users. Only a server, as we'll see, needs to ask for a very specific or particular port number. The idea is when you write a client program, you don't really care what your address is. You care what the other end is. If I have a web browser and I fire it up and I want to go see, a web page on google.com, what I need to know is the address of google.com, and I need to know the port for the web browser to connect to. Now, if I don't specify a port in a web browser, it'll use a well-known port for web servers, and that is port 80. And we'll show you that, and we'll demonstrate that in a minute. Well, the idea is that, if you're a client and you don't care about the port number, you can just ask the system to say, or just give me any old port number so I can talk to a server. And then we'll see they use the word bind, or bound, okay? What happens is a socket has to have an address bound to it, and that address has to include a port number. And as we'll see, we can explicitly bind whatever one we want, which is what a server would do. And as we'll see, that there's a way to ask the server what port was given to you if you said, I don't care. Once it's bound on there, you can ask, what's the name of my socket? And then remember, the name in this context is, we'll see the IP number and the port. And now we get to the good stuff. Connections, or what they call a stream. And the narrative continues. To initiate a connection, we simply create a stream socket. Then we'll call connect if we're a client. And that will specify the address of the socket that I want to connect to. Provided that that target socket, that is namely one of a server, provided that exists and is prepared to accept a connection, that connection request then will complete and the program can begin sending messages. As I said before, those messages will be delivered in order, but they won't have boundaries. And again, the boundaries refer to the fact that if I write 10 bytes and then I write 20 bytes, the server might get 30 bytes in one single read call. Or it could just as easily get 3 sets of 10 in 3 separate read calls. When you're done, the connection is then destroyed when one end closes the socket. Now, by default, if one end closes it and the other one keeps writing, you'll get what's called a SIG pipe. And by default, your process will die. So you have to take care of this situation if it matters to the design of your application. And as they continue to describe down here, unless you actually do that, it will end up killing your program, and it will most likely print a message like broken pipe as your reason for error. Now, they observed that the connection for a streaming socket is asymmetric. And that is that one end, as we'll see in Figure 7a, is what we're going to see is going to be called a client, right? The client will request a connection to be made to a particular socket on a server. The server will then be the end that accepts such connection request. Continuing along, we see that the program in Figure 7b, and these are the programs we're going to look at. The Figure 7a, the client, and Figure 7b is what we're going to focus on for the rest of this discussion. This notes that 7b is a rather trivial example of a server. It creates a socket, and it's going to bind it to a name specifically so that we can set its port number so that the clients can know what port number to use when it wants to connect to it. Then to accept the connections from the client, it has to call a function called listen. Right? It listens, we say, for connections. If a connection comes along, we will see that the server will accept the connection that has been requested. Once the connection has been created, the server will simply print out the data that comes from the client. All right, so as you can see down here, there is the initiating end, or specifically the client, where we said it calls connect to the server. When we're done with that, we'll see that it will write some data to the server and then close the socket down here. If you look at Figure 7b, what we have here is a server that's set up. You'll see it calls bind. It then says get sock name to figure out what port it was assigned, okay? Because in this case, we're not going to bind any particular port. I'll talk a lot more about that in a minute. But from the bird's eye view here, we're going to ask, by the way, what port number did I get? So that we can print it out here so that we can start up a client and know what port to connect to. The server will then listen for connections and go into a loop. It calls accept to accept any new connection that comes along. And as we'll see, it will read data from that connection, print it out in this loop down here. Okay? The key here is that accept is a blocking call. Listen is not a blocking call. Listen says, set me up so that if someone wants to connect, I can accept the connections by calling accept in the future, where the future is on another line of code other than the listen, okay? Now we enter in an infinite loop here, as we'll see that it will wait for and accept a connection that comes along. And as I just showed, it'll read the data from the socket. And if there's no errors or anything like that, it'll print out what it got until the read function here returns 0, which is what it does when it represents an end of file. Okay? When that's done, it'll close it. And this while true down here is the bottom of an endless loop up here that says do. All right? Now, this is like over a bunch of pages and kind of hard to read. So I took the liberty of cutting and pasting this code into regular old files so we can run them and see how they work. Let's start by looking at the client program. First thing we notice is I've made modifications to this. Why? Because 35-year-old programs written in C to run on BSD Unix won't run on a modern Linux operating system, okay? Now, okay, so what did I do? I added string.h because some of the stuff is defined in string.h that we're going to use here. This is the string that's right out of the original code. So this is the message that's going to be sent from the client over to the server, all right? What else did I change? Well, this is the modern way of writing a C function or a C++ function, where we put the arguments in the parentheses. The version in the book uses the old K&R style, where these arguments are listed below the main. But don't worry about that. These are just cosmetic changes over the years. Now, this one's a little bit more subtle. When these so-called socket addresses, right? The server here, if I scroll back up, I went too far. This socket or IN structure, that thing represents the, as you might guess, the socket address, okay? The underscore IN means that that socket address is to be used with the Internet Protocol. There's different kinds of sockadders, okay? And here's the problem. One, the Berkeley socket API calls have no standard C++ libraries to ensconce them. So you end up writing C function calls in your modern day code. Usually people will either create their own library, or they might download a library with a name like Boost or something like that, where someone else has written a set of classes to wrap these things up so that you can use them more as C++. But the bottom line is that as of today, in 2021, there isn't an official standard way of talking sockets with C++ programs. So we're going to use the C functions. And because C does not provide a way to implement inheritance and virtual functions and stuff like that, we have to kind of make do with the way that such a thing is done in C. Okay? No polymorphic types. We have explicit structures with no inheritance. So what do? You have a whole bunch of different sock adder type structures. And then these functions like connect are passed the specific type of sock adder structure, but you gotta cast it to be a generic sock adder structure. All right? This is not a huge deal. You just got to remember to cast these things when you call these lower level library functions. All right, so let's add some doc here. What is this? This is the file descriptor for the socket connecting the server, okay? As we'll see, this is the lowest level object in the library hierarchy. The lowest level C calls use an integer value to represent each one of the files that's opened by the running process. Okay? This down here, as the name suggests, is going to be the socket address for the server connection. This down here, we're going to use this to convert an IP number into the sock adder structure, okay? All right, so the first thing we need to do is come down here and we need to create our socket. We say, I want to use the INET address family. You just put AF INET in here to say, I want to use the Internet Protocol version 4. That's what this thing represents. That's the one that we're all familiar with, that has the 4 numeric values with the 3 dots between them. Sock stream here means I want a streaming connection, which will use the TCP protocol when it creates this socket here. 0 over here, if you look at the documentation for the socket command, allows you to, if you really want to, tell it specifically that you want not only a streaming connection, but you want to use the TCP protocol. 0 simply says use the default, which is then the TCP protocol. So this is normally how you see sockets getting created, okay? If it ever returns a value that's less than 0, or specifically -1, it means that the socket could not be created for whatever reason. The p-error library call is very commonly used in older code. What you see is you give it a string here, which is a message you want to print if there's an error. And what it will do is it will print out your message, a colon, and then it'll print a descriptive message based on the current error no value, okay? So basically these low-level functions all set this thing called error no. It's spelled like this, okay? ERRNO. And this little library routine down here will print out something that describes that error number, like I said, along with your little message here, okay? And exiting in anything with a non-zero value means that the program has died and that the shell or the command environment that ran it should react accordingly, okay? So this is how you create a socket, as the comment says, okay? The next thing you want to do is create this sock adder IN object and initialize it, okay? Now we know that if our end of the socket is an AFINet sock stream, then we know that we want the other end to also be AFINet, all right? This has to match. If I want to talk a streaming protocol, which means TCP, using Internet Protocol version 4, which is what this means, on my end of the connection, then I need to make sure that the other end matches. Otherwise, it won't work, okay? This call here is a little bit arcane. I'll show you in a minute how we do this today. But the bottom line is it takes the first argument that's passed to the command, which we'll see. We're going to type in an IP number in there. And it will convert that into a structure called a host ent. Now, getHostByName returns the address of a host ent object. Now, if you're, advanced programmer, you should spot something here that's kind of a problem, okay? Either something's wrong or this is not a reentrant function, and the latter of the two is actually correct, which is why most people don't use it anymore. But that's not really important right now. The bottom line is this thing returns a pointer to a host ent object. And if that pointer is null, it means it couldn't find the address of the host. So we're going to print out a message. Hey, I couldn't figure out what host that is. And this is the C-style way of printing a message to the standard error. Like in C++, you might say something like this. C-E-R-R, double left, and then say argv1. And then your message over here, unknown host, okay? Just so that you can follow along. We could port this to C++ if we wanted to later, but the bottom line is if you see things like printf and fprintf, what happens is if you see a %s in here, it means that there's an argument over here that's supposed to be a C string. And take the value of that C string and put it in here. In this here, that's kind of like a template to format the output. If you've never seen that before, that's what that means, okay? And obviously, if there's an error, we print out a message. We want it to go to standard error, and we're going to return a non-zero exit value. Now, if it's not null, we can go ahead and grab out this thing called the address, okay? We're going to say copy. This is an arcane version of a function. Nowadays, we would use memcopy or some other way to do this. But again, you can just read the man page how this works. Well, only difference is that the source and the destination arguments are flipped around in the other order. But otherwise, it's like memcopy. Point is, we take this field from the host ent object, and then we need to copy it into our sock adder IN object up here, along with the protocol family, all right? We want to use IP4, and we want to connect to a server that has this address, okay? Now, the address here is an object that has an arbitrary size, and that size is based on the kind of address family and protocol you're using. So the bottom line is, we need to get the address portion of the host ent, and we need to copy it byte for byte into the address portion of our sock adder IN. When we're done with that, we also need to put the port in there. Like the document said, we need to have an address, we need to have a port, and we need to have the protocol family. Those three things represent the socket, okay? So there's our protocol family, the address, and we need to put a port on there. Now remember that this thing represents the full address of the server we want to connect to. We don't care what the address is that this client is going to use. Like I said earlier, we're going to just use a wildcard and say, I don't care. We're going to just use the socket that was created that has nothing other than simply the address family and the fact that the protocol type is a stream. In other words, it has no address and it has no port for the local end of the connection. but the end on the server, the remote end, will have a fully specified name, as the document put it, but what I would call this sockadder IN, okay? Down here, the client calls connect. It wants to connect the file descriptor represented by this variable here, the socket that we created up here, okay, to the server whose name, the sockadder IN, was created up here. And because C does not know how to deal with polymorphic types, we have to cast this to a generic class called a sockadder. And because then it does not know the actual size of the real object, we have to pass that as well, okay? If you're not following along, don't worry too much. You just simply have to send a pointer to the thing that is going to be used as the address of the server, as well as the number of bytes that that thing occupies, okay? If that fails, it'll return a -1, and we print out an error message and exit the program. If it works, we're going to use the write system call, which is the lowest level that we can have, to write into this socket the text from this data macro up here, right? You saw that with the quotes up here. We're going to write this string, this hard-coded string, over to the server, and the way the write call works is you have a file descriptor here, you have a pointer to a binary set of bytes, and then you tell it how many bytes you want to send. Now remember that a size of, when applied to a C string, includes the null byte at the end of that string. Okay, this is kind of subtle if you're not used to working at this level. And we'll see how that reveals itself in a few minutes when we look at how the server works, okay? And of course, if that thing should fail, it'll write out an error message down here. Whether it fails or not, we close the socket and end the program. So what's wrong with this program? Well, you have a main that's declared to return an int, but there's no return statement down here. Like, you should at least say something like return 0 or exit or something like that down there. We'll also see that the write call may or may not write all of the data, this many bytes, out in one call to write. So this is really sloppy, okay? What its purpose is to discuss the stuff up here. Not so much what's happening down here, okay? So it's sloppy, but we'll see this works fairly well. Now remember, I saved it in a C++ file, and I've got my warnings and all that set up pretty high. So this is going to do a fairly good job at error checking that code. Now, if you're going to write a client and a server, and you make mistakes, which every programmer does, it makes it very difficult to debug what's going on when you have two programs that are communicating with each other, when you don't really know which one of them is broken when the thing acts in a strange way. So let's look at a utility program that's pretty handy here, okay? Let's use a program called netcat. Now, netcat is very commonly available on most Unix systems. I honestly don't know if it's on Windows, but you can log into a Linux box or a Mac and use this without a problem. The way it works is you can create a server or a client with it without writing any code at all. So if I say -L, 1, oops, if I can type, 1, 2, 3, 4, 5, like this, what I'm doing is I'm saying start up a server and listen for connections on port 1, 2, 3, 4, 5. If I go up here and I say netcat 127.0.0.1, 1, 2, 3, 4, 5, what I'm going to do is I'm going to create a client that's going to connect to a server at this address right here with this port number, okay? Because this one's listening on 1, 2, 3, 4, 5. I can connect to it, and I can send a message. And when I'm done, I can hit Control-C to terminate the client. I'll talk a little bit more about the mystery of the 127.0.0.1 in a minute. Meanwhile, be it understood that I can use netcat to start a server, and I can use netcat to start a client. The point is, if I start up my server again here, And I let it run on 1, 2, 3, 4, 5, and then I run my client program that we just compiled to 127.0.0.1, and I say I want to connect to 1, 2, 3, 4, 5. What'll happen is our client program will connect to a server. We don't have to write one. We can use this as a test server that will simply print out any message that arrives, okay? And remember, our client sends a string that says, you want a half a leg, and so on, right? So if I run it, you see that's exactly what happened. Half a leg, dot, dot, dot. Now, why is this way over here? It's because when the client program ran, it did not put a carriage return at the end of it. So let's go ahead and add one, among other things, right? Okay, let's go ahead and clean this up a little bit. It would be nice if you did this that you can actually print it out. Let's go ahead and restart our server again and rerun our client. And now you see we sent a string and we sent a carriage return at the end of it. And the server then print out the whole thing. The client, of course, closes it and the server goes away when the socket is terminated. Now let's do this so we can take a much closer look at what exactly comes over that connection. All right, so what do we got? We see all the hex values, half a leg, dot, dot, dot. Okay, and then we see these other two dots. Well, we're looking at a hex dump. That's because these last 2 bytes are not printable, so it prints out a dot, okay? Now remember what I said about the size of on the double-quoted string would include the trailing null in a C string. There's your trailing null right there. So that null went over the socket, and the server did indeed get it, and it did print it out with that null right there, okay? Now that's important to keep in mind when we start looking at how this server demonstration code works in here, all right? Again, we'll get back to the IP number in a minute. Here's the main of the server. This one does not take any arguments at all. We see pretty much the same kind of stuff, plus a little bit more going on in here. We have a buffer and some other things going on. Creating a server in IP version 4 works just like this. Create a socket that runs an AFINET, which is 4, for a stream. And notice that when we create our address here, this address is going to be this socket end of the server, not the client. All right, so the server creates this socket so that it can listen for connections that come along. This is the one that we have to get more specific with. And by that I mean the server has to bind a name onto its socket so that we can know what its address and port are to tell people that want to run a client that can open up a socket and talk to our server, okay? Now, the way this is going to work is we're going to say we want to run protocol version 4. We don't care what our address is, and we also don't really care what port we're going to use. Okay? This is not really common for servers, but it's certainly something that you can do. And then you can bind that address or that name onto the socket. All right. Now, what does it mean to say I want IP version 4? That's really the only thing that we've specified by leaving the other ones, these so-called wildcard values. Okay. What will happen is the machine will bind any and all addresses that your host is known as, and we'll talk about that a little bit more in a minute. And we also said we don't care what port number will be bound. Okay. That's what this all means. And again, we have to cast this because we don't have polymorphic data types. The bind, if it succeeds, will return a value of 0. If it returns a non-zero value, it will have failed, and we do the usual error and exit out of the code like this, all right? So let's look and see what happens now. Here's the get sock by name. We saw it in the narrative earlier. It says, you know, if you have a socket and you want to know the name that was bound onto it, like the address and the port in particular, we really want to know what port was bound, okay? We can get it by using get sock name, specifying the socket. We have to give it a sock editor. It's going to fill this in, all right? Now, we're going to just reuse the one that we used up here. Why? Because we're done with it. We're going to throw it away anyhow. So this is going to overwrite that same socket. And just like before, we got to cast it, and we got to give it the length like we did before, but this is a little bit different. You see, we give it the address of an integer or as we'll see, a sock len t up here, right? The length variable. And when we say get sock name, we need to store the number of bytes in this object into a variable of that type and pass the address of that variable into get sock name. Again, because C does not have polymorphic data types, so that get sock name knows how many bytes there are in this object. Now, the reason we send it as a pointer is because when get sock name is done, it might change the length to a smaller size if it wants to let us know how much of this object it filled in. But this is what you get if you don't have polymorphic types, okay? Again, it's just boilerplate. We just use it the way it is. Now, once we get that name back, we can print it out like we saw before. This is the template. The socket has port number, and then this is a %D, which means it's going to print out an integer value and a carriage return after it, all right? So what the heck is this all about? Well, it turns out that the value inside this object is in what is called network byte order, which is big endian. If your computer does not use big endian for its data types, you have to convert this from big endian to little endian. And on an Intel box, you got to do that. So what you can do is you can use this macro here. It's called network to host short. If you don't remember to flip the bytes around, then it will simply print out the wrong value and get very confusing. All right, once we've done all that malarkey up there, what do? Okay, we want to listen on that socket that we've got all set up. And we enter this endless loop down here. We're going to accept a connection on the socket that we just set up. And if there are none ready to go right now, the program will sit here blocking forever, waiting for a client to do a connect to the address with the port that we printed out up here. Now, if accept fails, it'll return a -1. We do the usual thing with a P error, print out a message. Otherwise, it succeeded. We're going to enter into a loop like this. And these are do loops, so they're bottom driven, right? What are we going to do? Now, we're going to zero out the entire buffer that we're going to use in this read call down here, okay? Now, if you've never used a read call before, what this does is just like the write. It says, here's the file descriptor. In this case, it's a socket. It's the socket number that was returned by accept up here. Read from my endpoint of the streaming socket. Put the data into this buffer. And this over here probably should have been a size of. And it will read up to 1024 bytes. If read has an error, it will return a -1 and print this message out down here. If it returns a 0, it means it got an end of file. It means the other end of the stream closed it. So it prints, I'm done now. Otherwise, it'll print out what the client sent over. Okay? Then we say, well, our value is not equal to 0. It's just going to go into this loop forever here. Okay? I suppose if it ever returned an error like -1, it would say, error while reading a stream message, and then it would print out this, even though it's an error, and it would not equal 0. So you get to this crazy endless loop. Like I said, this is not the greatest code in the world, but it just simply demonstrates in the crudest fashion how you can use a socket to send a message and then shut it down and go on your merry way. I put a comment over here saying this is just awful because what they've done here is they've zeroed out this entire buffer every time they read any data in over here. All right, this is 10 tons of cure. It'll work. It's okay. And of course, they use B0, which is the older version of call. Today, you would use memset. Anyway, the bottom line is that we may or may not get all the data in one single call to read like we sent in one single call to write on the other end. And just like the other end may or may not write the entire message, or it might send it over in chunks, read also may not read the whole message on the first call. It might take multiple calls to read in order to receive all the bytes in that message. It definitely will if the writing end sent more than 1024 bytes, okay? Because this will read up to that many bytes. If it doesn't get out at all in the first try, it'll return a non-zero value representing how many bytes it did get. It'll print it out and go around this loop and print out some more later. Okay? Now, why do we have to B0 out the entire buffer? Well, if it turns out the buffer has garbage in it, and you read stuff into the buffer that does not have a null at the end of the buffer when the read call is done, and you try to print it out, it might print all kinds of garbage forever in the memory of the machine that might follow the end of this buffer, okay? In other words, this could be an unbounded amount of data coming out of that print statement, all right? Again, this is all very old school stuff, and it's due to the fact of the way that read and write calls work. They are not mandated to deliver or transfer as many bytes as you ask in any one call. It could always give you less. So, while the client did send over a bunch of characters and a null character at the end of it, if read got all of it in one call, this could be counted on as printing the entire contents of the buffer and hitting the null that the client sent over to terminate that string. Okay, that's the point. And the same thing would happen in C++. If you wrote C out double F buff, it would screw up too. So this is not just a C problem. This is what happens as a feature of the read call. So by setting the entire buffer to 0 first, you're guaranteed that if the message that was sent to you does not have a null character at the end of it, at least there will be null characters in this buffer after whatever you did receive. Okay, that's why this thing is in here. Now, why do I say this is awful? Well, I say it's awful because, obviously, if rval tells you how many bytes were received in this call to read here, if you read in 1023 instead of 1024, there'll always be room for one null at the end of whatever you've received. And down here, before you print it out, you could have just as easily said buff, open square bracket like this right here. You could put some curlies down here. You could say buff sub rval equals a null character like so. Oops. And then print that out like this. Now, this is kind of a messy format, but you could do this like this. My point is, putting one null byte in here is a lot more efficient than putting 1,000 in there every time you go around this loop. Because the only time you know you need to have a null in there is if you want to print it out, and the only place there has to be one is in the one byte after the message that you receive from the client. If the client includes a null in their message, that's fine anyway. The buffer will be terminated before you got to your null, but you're guaranteed either way to do it this way. So this is just a more efficient way to do it, in my opinion. I'm going to undo this and go back to the original code. All right. This will run, but I personally think this is a bad choice. Let's go ahead and compile up that server. Let's grab our other window here and run the server program. All right, now you see we ran it. It says, hi, I'm bound to this port. Let's kill it and start it up again. We might see it gets another port. So every single time we run it, it's going to be bound to a different port because we didn't bother to tell it which one we want. It said, just give me any one. All right, now let's run our client again. And connect it to 57247. And we can see, voila, have a leg, dot. Remember, we had put a carriage return in there. And then a null. So it did get the entire message in a single call to read. So every time we run this, it'll just send out the same message over and over again. We can also use the netcat client application and connect to that same port, 57247, and say hello. Now notice that the characters aren't going out as I type them. That's a feature of how what we call cooked I/O works in the netcat client application. But it will send it all out when I hit carriage return. So goodbye. Hit carriage return here and Control-C to stop the netcat client. Now you'll notice that the server said ending connection. It printed out hello and then goodbye, and ending connection. This thing is going to keep allowing me to reconnect and start up more clients. Okay? Which is normally what you really want. If you have a server and it allows you to connect and reconnect, it becomes serially reusable. That way a client can connect, it can have a conversation with that client. When it's done, the client disconnects, the server can be reused to support a conversation with a different client. All right, now let's talk about this mystery number, this 127.0.0.1. Where did that come from, and why did I know to use that number to connect my client and server together? Well, if you type IP adder on most Unix systems, it'll tell you how it connects itself to the TCP/IP protocols on the internet. Now, there's a lot of stuff here. The only thing we're really concerned about is the fact that I have this 1 colon and a 2 colon down there. That means I have 2 interfaces on this machine. This is a machine on my desktop. It has a physical hardwired cable that goes into the router for my internet provider. This interface number 2 that says ENP5S0 just so happens to be that interface that has the wire in it that connects to my firewall. The IP number for my machine is this number right here, the 192.168.2.106. This /24 has to do with something else I'm not going to talk about right now. This is one address that represents my machine. The fact that it says INET over here means that this is Internet Protocol version 4. Okay? This one down here that says INET 6 is Internet Protocol version 6, and this is an INET 6 address. It looks like this, right? It has colons with 4 hex digits between each one of those colons. So my machine is known as this address to any machine that wants to contact it via IP4. It's known with this address if a machine wants to contact it using IP6, provided that they want to talk to my machine by way of the wire that's plugged into this physical connection on my box. Now, if you were to run this on some other machine, this name here, the ENP5S0, this name here would change probably. It'll be based on like the kind of card or the motherboard that you have on your computer that has that hardware interface on it. Okay, this is basically like the driver name. Now let's look closer at link 1 up here, LO. This is what they call a loopback interface. This, in every machine, everywhere on the internet, if it speaks IP version 4, will always have an address that says 127.0.0.1. You can always use this address if you want to open a socket and connect it back to yourself. This is what we call the loopback IP number, or sometimes it's called the local host. Now, if it wants to use a protocol that is implemented using the Internet Protocol version 6, it would use an address that looks like this, ::1. Now, if I was to log into another box, like Hopper, out at Northern Illinois University, and ask it what its addresses are, I end up seeing this. Look at this. Here's the loopback interface, and once again, the IP4 number is 127.0.0.1. INET 6 is ::1, and instead of only having one cable connected to it, this one actually has 2. So this one has 2 different ways of contacting it from the rest of the internet. And as you can see, here are those IP numbers in Protocol 4, and here's the Protocol 6 version of the IP numbers that could be connected to these machines as well. If we then go on to another machine, and we ask, what are the addresses on this one? Again, we see loopback 127.0.0.1 and ::1 for IP6. We also can see that it has 2 different ways to be connected from the rest of the internet as well. We'll also notice that this internet address in IP4, 10.158.56.120, looks a lot like the number we saw up here, but notice it ends differently. So these 2 numbers might look the same, but they are unique and differ by almost 100 in this last number over here. All right, let's summarize what we know so far. If we have a computer like the one on my desktop, it has a loopback address, which is always going to be 127.0.0.1, no matter what. And it is way a client application that runs on my machine can connect to itself. You can say, I want to connect to me. All right. And I can use this IP number, the address of my machine, or the server-side socket address of 127.0.0.1 to refer to myself. If we have another machine on the internet, say google.com, their main web server, it also will have a loopback interface. If they run a program on their own server that wants to connect back to itself, it too would use 127.0.0.1 to refer back to itself. Okay? Now, my machine is also connected to the internet. Very common to draw it this way. The internet is oftentimes just a cloud, a network cloud. It's somehow my machine goes through many phone companies and so on, and then pops out the other end. It can connect and talk to Google. It can also go to Netflix and any other site that I've ever used on the internet are all, graphically, conceptually drawn in this cloud. All right? As we saw earlier, my machine's address of its physical connection that goes to my internet provider is 192.168.2.106. Now, normally when you connect to Google, you don't put a number in there. You use this name. And I'll show you in a minute. You can look up the number that corresponds to this host name. Okay? There's a database out there. It's called DNS, which stands for, unfortunately, Domain Name Service. And these domain names are these host names that you're familiar with seeing, not the network domains like the IP protocol 4 and so on. All right. So, like I said, the notion of a domain name is got two different meanings when we're dealing with the internet. Now, as we saw, in order to run a server on my desktop, I need to specify three things, and that is the protocol address family, which is implied by these numbers because these are IP4 numbers, and we have to give it the IP number, and we need to give it a port number. Those three things together represent the address of a socket that is bound to an IP4 address, okay? Now, if I just start up a test server, I can fire it up on any port I want. I can give it a port number like we did when we used Netcat, or I can say, I don't care what port it's on, just connect it to anything available right now and tell me what it is, and then I can print it out like we saw with the test server program from the IPC tutorial book. Now, as an example of what we call a well-known port number, well-known service is the abbreviation you oftentimes see. Port number 80 is reserved as the well-known service called HTTP, which is the port for what we'll see is an unencrypted connection to a web server. So when you go to your web browser and type in google.com and like nothing else, what it's going to do is it's going to open up an IP4 socket or IP6, depending on the kind of addressing that your machine uses. It'll open up a socket, a streaming socket, a TCP connection to a google.com server, and it'll use the HTTP protocol. It'll send a message over there. It says, hey, I want to see a web page, or I want to do a search, or whatever you want to send over there. And it'll then respond back with a web page that'll be showing in your browser. Why don't we look more closely at this using our Netcat test program? All right, so what's the first thing we need to do? If we want to connect to google.com, we got to look up its IP number. You can say dig google.com. This is one application that runs on most Unix systems that allow you to inquire as to all the IP information about this machine name. And it'll come back and say, okay, I asked it. There are a bunch of technical details in here. But the bottom line is that it says that google.com is an internet address, IP4 address, which is that number right there. And since we know that port 80 is for an unencrypted web server, we can do this. Now, it just so happens that the unencrypted connection is just simple ASCII, and I can type in the same thing that a web browser would send to request a web page. For example, one standard request would be to ask for the heading information of a web page. And the way you do that is you type head, you ask for the web page, slash is the home page, and you tell it what version of the protocol you're going to use. Then you send it a blank line, and it'll then come back with a response that says the status of your request. It says, okay, I got your message, and I'll tell you what you want. And if I wanted the entire page, I would use a different command. But this is just the heading of the page, which tells me about the page. It'll say if I actually get the data, it'll be in HTML format, it'll be an ISO 8859-1 character set, and it says all this other stuff and cookies and all these other things, all right? Now, when I'm done, I can send another blank line, and it'll close the socket on me because that's the end of that conversation. Now, the point of showing you this is to demonstrate that even most complicated things are still based on this most simple concept of these TCP streams, port numbers, and IP numbers. It's just a matter then of knowing what the protocol messages look like and how to interact with them once the socket's open, all right? It turns out that HTTP is specified in open source, freely available specifications at a place called w3c.org. If you do a Google search on HTTP protocol, you're going to find links into here, as well as other places like RFCs, which stands for Request for Comments. And those have detailed information about how various protocols work that are used on the internet. Now, I think this is as good a place as any to take a break. We'll come back later with part 2, where we walk through a upgraded version of the example programs from the IPC tutorial chapter of the program or supplementary documents that we've been looking at. Thanks for watching. See you next time.